Hello, welcome to 6.3, Separation of Variables. I know in the last section we talked about separation of variables. We did that to a smaller degree. Here we're going to go a little further with that. So separation of variables. Consider a differential equation that can be written in the form m of x plus n of y dy dx equals 0, where m is a continuous function of x alone and n is a continuous function of y alone. The x terms can be collected on the right side. You can move that mx stuff over to the right side with the dx, and the y terms with the dy on the left, and you can integrate both sides. These are called separable equations, and the procedure to find the solution is called separation of variables. So we're doing a little more with differential equations here. So our original differential equation, x squared plus 3y dy dx equals 0. You can move the x squared over with the dx. Sine x, y prime is cosine x. Move the sine x over. This is dy dx. So dy is cotangent, which is cosine over sine dx. X, y prime over e to the y plus 1. Divide both sides by x and bring the dx over. You'd have 1 over e to the y plus 1 dy equals 2 over x dx. So example 1 says find the general solution of the differential equation. Dy dx equals 3x squared over y squared. So y squared dy would be 3x squared dx. The integral of y squared dy equals the integral of 3x squared dx. So y cubed over 3 dy equals 3x cubed over 3 dy is gone. 3x cubed over 3 plus c. So obviously those 3's are going to go away. I'm going to call that c1. If I multiply both sides by 3, y cubed equals 3x cubed plus 3c1. If I bring the x and the y over to one side, y cubed minus 3x cubed equals, let's call it c. So we'll call this part just some constant c. And there you go. Let's scroll this up. So we have dr ds equals 0.75. Should be, that's right, 0.75 r. Okay. So 1 over 0.75 r equals dr equals ds. In fact, I'm going to do it this way. I'm just going to say 1 over r dr equals 0.75 ds. So the integral of 1 over r dr equals the integral of 0.75 ds. This is natural log of the absolute value of r equals 0.75 s plus c1. So so the natural log of the absolute value of r is e to the 0.75 s plus c1. So r equals e to the 0.75 s, e to the c1, and we'll call e to the c1, call that c. So that r equals c e to the 0.75 s. Excuse me, didn't get to the microphone in time. Try to cover it. Okay, moving on here. This is find the particular solution that satisfies the initial condition. Square root of x plus square root of y prime equals 0. I'm going to move the square root of x over. We'd have square root of y prime equals square root of x. So square root of y dy equals square root of x dx. So the integral of the square root of y dy is the integral of the square root of x dx. So just integrate both sides. This becomes y to the 3 halves over 3 halves equals x to the 3 halves over 3 halves plus some constant c1. I'm going to multiply everything through by 3/2. And we have y to the 3/2 equals x to the 3/2 plus, call this just c, some new c. And we have our initial condition, y of 1 equals 9. So 9 to the 3/2, I'm putting 9 in place of the y, equals 1 to the 3/2 plus c. So the square root of 9 is 3, 3 cubed is 27, equals 1 plus c, so c must be 28. We have y to the 3/2. I have a negative issue. Forgot to subtract that. There. Negative there. There we go. Negative 1 plus 27, there we go, 28. So y to the 3/2 equals negative x to the 3/2 plus 28, or y to the 3/2 plus x to the 3/2 equals 28. Okay, I'm going to go on to part B now. It says dr d theta equals e to the r minus 2s. Sorry, dr ds equals e to the r minus s. So you can write this as dr ds equals e to the r over e to the 2s. If you bring that over, switch them around, e to the 1 over e to the r dr equals 1 over e to the 2s ds. And you can say e to the negative r dr equals e to the negative 2s ds. Integral of e to the negative r dr is integral of e to the negative 2s ds. Integrate that, you can have e to the negative r over negative 1 equals e to the negative 2s over negative 1 plus some constant c1. So e to the negative r equals e to the negative 2s plus negative 1 times c1. So that e to the negative r equals e to the negative 2s minus, just say plus some other c. R of 0 is 0, so e to the 0 equals e, sorry, this 0 goes here, that 0 goes there. E to the negative 2 times 0 plus c. So 1 equals 1 plus c, which means that c must be, oh, I integrated wrong, didn't I? That should have been divided by 2, negative 2. Okay. So c is 1/2. So e to the negative r equals e to the negative 2s over 2 plus 1/2. Now I want to solve for r, so the natural log of e to the negative r is the natural log of e to the negative 2s over 2 plus 1/2. That's always positive. So e to the negative r, no, just negative r, is natural log of e to the negative 2s over 2 plus 1/2. So r equals negative natural log of e to the negative 2s over 2 plus 1/2. Bring this one as a power, the negative out front as a power. R equals the natural log Oh, before I do that, I'll do this in the same step. E to the negative 2s plus 1 over 2, negative 1. So r would be equal to the natural log of 2 over e to the negative 2s plus 1. There we go. Okay, I'm going to go on to example 3 now. Find the equation of the graph that passes through the point and has the given slope. So our slope is y prime, that slope is negative 9x over 16y. So think of this as dy dx equals negative 9x over 16y. This part's going to go over there, this part's going to go over there. So 16y dy equals negative 9x dx. The integral of 16y dy is equal to the integral of negative 9x dx. That's going to be 8y squared is equal to negative 9 halves x squared plus c, 1. No, it goes through 1, 1, so 8 times 1 squared equals negative 9 halves times 1 squared plus c1. 8 equals negative 9 halves plus c1. If we add 9 halves to both sides, c1 equals 25 halves. So we have 8y squared equals negative 9 halves x squared plus 25 halves. We bring this over, 8y squared equals, plus 9 halves x squared equals 25 halves. Now if I multiply through by 2, I have 16y squared plus 9x squared equals 25. So we can write 9x squared plus 16y squared equals 25. This would be the equation of an ellipse divide everything by 25. Okay, moving right along. Let's talk about a homogeneous differential equation. Okay, homogeneous differential equations. These are differential equations that are not separable in x and y and can be made separable by a change of variable. This can be seen in the form y prime equals f of x, y, so it's a function of two variables, where f is a homogeneous function. So a homogeneous function of degree n, the function given by f of x, y is homogeneous of degree n if f of tx, ty is t to the n f of x, y. Okay, example 4. It says determine whether the function is homogeneous, and if it is, determine the degree. So let's see, f of tx comma ty, it's going to be tx squared ty squared over the square root of tx squared plus ty squared. So I'm putting ty in place of the y's, tx is in place of the x's. So we have t squared x squared, t squared y squared over the square root of t squared x squared plus t squared y squared. So it's t to the fourth on top, x squared y squared over, you can factor out a t squared down below. So f of tx comma ty is t to the fourth x squared y squared over t times the square root of x squared plus y squared. So the t's reduce. You have you have t cubed x squared y squared over the square root of x squared plus y squared. And that looks a lot like what we started with. That would be t cubed times f of x, y. So this is homogeneous of degree 3. Okay, now let's move on here and talk about a homogeneous differential equation. A homogeneous differential equation is an equation of the form m of xy dx plus n of xy dy equals 0, where m and n are homogeneous functions of the same degree. Theorem 6.2, change of variables for homogeneous equations. If m of xy dx and n of xy dy equals 0 is homogeneous, then it can be transformed into a differential equation whose variables are separable by the substitution y equals vx, where v is a differentiable function of x. Okay, so example 5. To solve the homogeneous differential equation, y prime equals x cubed plus y cubed over xy squared. Okay, so I'm going to bring this term, the denominator, over, and we'd have xy squared dy equals that part x cubed plus y cubed dx. If we say y equals some vx, our dy would become x dv, since v is a function of x, plus v times 1, so v dx. So x y squared, that's going to be x times vx squared, dy is x dv plus v dx equals, over here we have x cubed plus vx cubed dx. So x v squared x squared times x dv plus v dx equals x cubed plus v cubed x cubed dx. So this is x cubed v squared times x dv plus v dx equals x cubed plus v cubed x cubed dx. I'm going to distribute this. X cubed dx plus v cubed x cubed dx. If I distribute over here, I'll have x to the fourth v squared dv plus x cubed v cubed dx equals x cubed dx plus v cubed x cubed dx. Now, I'm going to subtract v cubed x cubed dx from both sides. And what are we left with? Come up over here. X to the fourth v squared dv equals x cubed dx. Now if I divide both sides by x to the fourth, I have v squared dv equals 1 over x dx. The integral of v squared dv equals the integral of 1 over x dx. So v cubed over 3 dv equals natural log of the absolute value of x plus c1. Now I'm going to the dv v cubed equals 3 natural log of the absolute value of x plus 3c1. And we'll call this just c. Now v cubed. Now y was vx, so v would be y over x. So y over x cubed equals 3 natural log of the absolute value of x plus c. So y cubed over x cubed equals 3 natural log of the absolute value of x plus c. Y cubed equals 3x cubed natural log of the absolute value of x plus cx cubed. There's your solution to this differential equation. Wow, fun. Go ahead and pause once more time on that one. I'm going to go down to example 6. There. Now I put on here the slope field that's associated with this problem. I actually took a picture with my web document camera, and I was able to crop it and put it into place here. I think that's what I did. I'm not sure. Anyway, this is the slope field. Slope at any given point of order pairs. So it says sketch a few solutions of the differential equation on the slope field and then find the general solution analytically. So if I were to start, like, I don't know, right here, it's kind of flat there, and it kind of goes down, comes down here, comes down, starts bending that way, kind of comes up, and looks like it makes a circle. Give it another one over here. Another circle. So make sure I'm staying within the dashes. So I'm guessing, just by looking at the way the slope field is and the way it tends to go around, I'm thinking maybe a circle. Okay, so if I bring the y over, we have y dy equals negative x dx. Integral of y dy equals negative integral x dx. So y squared over 2 equals negative x squared over 2 plus some constant c1, meaning y squared equals negative x squared plus some other constant c. If we bring the x over, we have x squared plus y squared equals c. That's the equation of a circle where c would be the radius squared. That was kind of fun. We have one more to do. One more page here. So pause if you need to pause here. A logistic differential equation. A growth model for an environment with a carrying capacity. Environments have carrying capacities. They can't sustain an infinite number of anything. Our planet can only sustain so many humans. I hope we never reach the carrying. I don't know. I don't want to say that in a negative way. I hope we don't reach a point where we're so out of resources people can't survive. But population would increase and start leveling off as you reach carrying capacity. Okay, growth model for an environment with a carrying capacity. dy dt equals k times y times the quantity 1 minus y over L, where k and L are positive constants, and L is the carrying capacity for the specific environment. If y is between 0 and L, the growth rate is positive. So if it's less than L, 1 minus something smaller than 1 is positive. But if it's bigger than L, 1 minus something bigger than 1 is negative, so it'll have a negative growth rate. The solution to the logistics equation is y equals and y equals 10 over 1 plus b e to the negative kt, and this might be one specific for the problem that we're doing. I think it's y equals L. I think this is an L over 1 plus b e to the negative kt. So find the logistic equation that satisfies the initial condition dy dt equals 2.8y times the quantity 1 minus y over 10 with the initial condition of 0, 4. So our k in this case is 2.8 and the L would be 10. Yeah, so that should be an L up there. So y equals 10 over 1 plus b e to the negative 2.8t. Now we're told initial condition 0, it should be 0.7, not 0.4. So 7 equals 10 times 1 plus b e to the negative 2.8 times 0. So 7 equals 10 over 1 plus b times 1. So 7 times 1 plus b equals 10. So 7 plus 7b equals 10. 7b equals 3. b equals 3/7. So our equations y equals 10 over 1 plus 3/7 e to the negative 2.8t. And that'll do it for 6.3, separation of variables. Well, I hope you enjoyed that. I hope you really consider taking differential equations as a class. And send me your questions. Thank you.